So, dear students, as you know that we have already discussed quasi-classical case in the classroom situation at the college, and we have done extensive exercises based on this quasi-classical case. Now, here in this video, I'll be discussing the adiabatic approximation, and I'll be discussing it within the purview of perturbation theory in general. And this concept refers to basically how system evolves when the Hamiltonian, when you have a Hamiltonian, when this Hamiltonian is changing slowly over a period of time. And such transitions, such that we have transitions between the quantum states, we have quantum transitions from one state to another state that we generally find. Now, the, it's better to make an argument on the adiabatic theorem, and this adiabatic theorem in quantum mechanics, it states that if a quantum system's Hamiltonian, if we have a quantum system, and the total energy of this system is given by the Hamiltonian, and if this Hamiltonian changes slowly, it changes slowly enough, and the system starts. It starts in an eigenstate, say some eigenstate n of this Hamiltonian. It will remain in this in this instantaneous state of the evolving Hamiltonian, provided no level crossing. I mean, there is no crossing. There is no crossing between the two levels. The two levels do not cross each other. However, this idealized scenario can be broken when transitions happen, when they happen between the states, say state n and state m. And certainly here the perturbation theory helps us to analyze these kinds of transitions, which are adiabatic in nature. Now, if I consider a quantum system whose Hamiltonian whose Hamiltonian as a function of time is t, and it depends on time and changes slowly. So the point is, it changes slowly compared to the system's intrinsic time scale. Now, in this case, the system starts in an eigenstate of some initial Hamiltonian. So we will have some initial Hamiltonian. So I would like to write that as h cap at some initial time t naught. And what happens is that this Hamiltonian, it starts with this eigenstate and evolves as this Hamiltonian changes. I believe that the key idea is that while the transition between different energy levels are suppressed, I mean, where we can think of adiabatic approximation like small transitions. There is a possibility of small transitions, and these small transitions can take place. They can occur, especially when the energy levels, when these levels come very close to each other. They will not cross each other, but they will come close to each other. Now, if we proceed from here to go with the concept, now let us express this Hamiltonian as h of t equals the unperturbed Hamiltonian with some lambda h1 cap and t. Here H naught is over, it's the unperturbed Hamiltonian. And this lambda H1 of t, it is basically the time-dependent perturbation, this lambda H1 cap of t. This is time-dependent perturbation, where this lambda is its value is less than 1, and this perturbation that's occurring here, this perturbation evolves. It evolves basically slowly in time. It evolves slowly in time. Slowly in time. Now, if I have to write down the eigenstate of this unperturbed Hamiltonian, the eigenstate of the unperturbed Hamiltonian will be h cap in a state n equals En, the eigenfunction or eigenstate n. Now, as the perturbation, this is our unperturbed Hamiltonian, and as the perturbation evolves, the actual state, that's linked with this, say the actual state psi of t of the system, can be written as the superposition of the instantaneous eigenstates at that moment of time. So this is our unperturbed Hamiltonian, and we can write down this state as the superposition of the instantaneous eigenstates, and for that, if I write down this state psi of t, it can be written as sigma n and Cn of t n of t ket. Now, what actually happens in adiabatic perturbation theory? The goal is basically to find the probability transition. We want to calculate the probability transition. And this probability transition is to be calculated between the different quantum states due to the slowly varying perturbation. Slowly varying perturbation. Now, to compute this, what we do is we simply solve the time-dependent Schrodinger's wave equation. So if I have to write down the time-dependent Schrodinger's wave equation, it is IH bar dou by dou t of psi of t. This is H, the Hamiltonian operator, at time t, psi of t of ket. Now, to focus on the transitions, we have two states here, the state n and state m. Now, in order to focus on the transitions between the two states, say I have the state n and I have the state m. Now, what we assume here is we assume that, so what we have is we have state n and the state m. What we assume is that the system, it starts from this state n. It starts from state n, and then we analyze. What we do is we analyze the probability of finding the state, finding the system in the state m. So also, what will be more precise here is that we are trying to analyze now. We analyze the probability of finding this system in the state M at some later time. At some later time. Now, the perturbation that's written down here as where is that gone? The perturbation, what's over here? This h1 of t. This perturbation, this h1 of t. What it does, it causes a coupling. Basically, it causes the coupling between these states, the state N and the state M. It causes the coupling between these states, and the probability amplitude for the transition is determined, and this is determined by the matrix element. So if I write down this matrix element as, say, M N at T, and this matrix element is M T, then the perturbation term of the Hamiltonian at T, and then N of T. So this is our matrix element. So this what we call this as the coupling. The perturbation that's there, it causes a coupling between these two states. The state, maybe this is state N and the state M. And this coupling between these two states and the probability amplitude for this transition that occurs is determined by this matrix element. And now for adiabatic perturbations, the transition probability from the state N to the state M, it can be easily derived using time-dependent perturbation theory. And the key result that we will obtain here, the key result that of this probability, suppose that is P, probability of this transition from N to M, as a function of t, what happens is that this probability depends on the rate. It depends on the rate at which the perturbation evolves and the energy difference between these two, difference between these two states. Now there is another important term here that we call as that's called Landau-Zener transition. Now let's first understand what this Landau-Zener transition is. One particularly important case of adiabatic perturbations is this Landau-Zener transition, which occurs when you have two energy levels, and these energy levels are approaching each other. They approach each other and they cross as a function of time. So they cross as a function of time. Now in this case, the transition probability between the two levels is given by this Landau-Zener transition, and we call this as Landau-Zener formula. Now, if I consider two states, if I assume that we have two states with energies, we choose two states with energies, E n of t, and the state as E m of t. And these two states vary. They vary with time. Now, if these two states come closer but do not exactly cross, they come closer and they do not exactly cross. They do not exactly cross. There is a probability here that the system will have a transition. They are not crossing over each other, but there is a finite probability that system will have a transition from one state to another state. So you can have a transition from the energy state En, from the state N to the state M. Now, this Landau-Zener transition probability for the system to stay in its initial state. This is very important. I'd like to write down this. I mean, the Landau-Zener transition probability for system to stay in its initial state. That is, what am I trying to tell is that not to make any kind of transition. If I represent that by P, and that I'll call as P stay, that probability comes out to be e to the power of minus 2 pi gamma. And this gamma is the probability density of this matrix element MMN whole square by h bar magnitude of V, where this MMN whole square, this is called coupling matrix. Now, this is called coupling matrix element between the states that are under consideration as M and N, and V is d by dt of Em of t minus En of t. Now, this is giving us the measure of the rate at which the energy difference between the two states change. So this Mn mod whole square is the coupling matrix. It's a coupling matrix element between the states, and this V is the change of the energy state from Em of t to En of t. Now, to have to write down the probability of transition, so this is what we have calculated here as the probability of staying the system without the transition. So if I have to calculate the probability of transition, that will certainly be the difference between 1 and the probability of the stay. So I can think of probability of transition as, so P trans, I'll call it trans, that will be 1 minus e to the power of minus 2 pi gamma. So gamma is already defined, and we can calculate the probability of transition from one state to another state. Now, let's quote an example. I mean, to better have an idea about what we have been discussing here. We have two cases. One is non-adiabatic case, and another one is adiabatic case, which we have been discussing. Now, if the perturbation evolves very quickly, if this perturbation evolves very fast, this is a non-adiabatic case. The system has a large probability to make transition from one state to another state, and in this case, this gamma that's over there, this gamma is small. And that means this P transition that we have written down here, this P transition will be nearly equal to 1 because this gamma is very small. And there is a very large probability for the transition to take place from the state N to the state M. So this is our non-adiabatic case. Now for adiabatic case, what we have now for adiabatic case, now the same thing, the perturbation evolves very slowly. Perturbation evolves slowly. That means this gamma that's over in that equation, this gamma is large. And if this gamma is large, then P stay. This P state, here I have P stay, and here I'm trying to talk about the P transition. This P transition is maximum here in case of non-adiabatic case where gamma is small, and P stay here is in this case this P stay is nearly equal to 1. Now in this case the system remains in its initial state. The system remains in its initial state as expected from the adiabatic theorem. So, this is the core idea between having a non-adiabatic approximation and the adiabatic approximation. Now, if we write down the formal transition probability in case of in adiabatic case, I mean, what we have is we have the time evolution of the coefficients. We have the time evolution of Cn of t. And this time evolution is governed by IH bar d by dt of this Cn of t, and this is equal to sigma m, the matrix element of H1 cap of t, and then you have m, and let's go with Cm of t. Now for a system that is starting in a state, say, that starts in a state n, the probability of transition to the state m can be written as Pn to m. That can be written as the magnitude of integral t naught to t, then m of say t dash, then h1 cap, then n of t dash e to the power of I integral en of t minus em of t. Now this integral depends on the rate at which the perturbation changes and the energy difference between the states and giving the transition probability. So with this, I would like to end this video, and I hope we will have a general idea about the adiabatic approximation using perturbation theory, and And to talk about this integral depends on the rate at which this perturbation changes and the energy difference between the states that are giving rise to these transitions. Now, to conclude this talk, I mean, using adiabatic perturbations, what quantum systems tend to stay in their instantaneous eigenstates. However, at the same time, the small transitions can still occur, and especially when energy levels approach to each other. The Landau-Zener transition is a prime example of how transitions occur between energy levels when the systems evolve, when these systems evolve slowly, but still allows for transitions due to the time-dependent nature of perturbation. So with this, I would like to say you goodbye.